The sun is the source of most of our energy here on Earth. Energy from the sun is used to produce electricity using photovoltaics and solar thermal plants. That same energy is also used for heating using solar domestic hot water systems, hydronic heating, solar air heating, and solar cooking, just to name a few. This video will talk about how the sun produces that energy. The sun produces energy using a process called fusion. Let's start our explanation of fusion with the atom. You've no doubt heard that everything is made up of tiny things called atoms. We'll use a very simple physics model to describe them. At the center of an atom are protons and neutrons. We call this center the nucleus of the atom. That's where the word nuclear comes from, since anything to do with nuclear deals with stuff in the nucleus of the atom. And to complete our model, circling around the nucleus are electrons. Different types of atoms have different numbers of these parts. This is one variation of a hydrogen atom, just a single proton and an electron. This is another variation of a hydrogen atom. It has a neutron added to the nucleus. This variation is called deuterium. And just to show you a more complex one, this is a carbon atom. So back to the sun and the process of fusion. For this we'll ignore the electrons since we're dealing with the nucleus of the atom only. The sun also is made up of atoms. Since the sun is so massive, it has extremely strong gravity, much stronger than the gravity here on Earth. This gravity pulls the atoms together. Normally the nuclei of the atoms don't want to get close together. The protons repel each other. But the sun's gravity is strong enough to overcome that, and when two atoms get close enough together, they merge, or fuse, to become a new atom. And that's where the term fusion comes from. So how does this produce energy? Well, take the example of our deuterium atom with its proton and neutron in the nucleus. Again, we're ignoring any electrons. It takes energy to hold neutrons and protons together in a nucleus like this. Let's make up a pretend amount for the quantity of that energy, 3. The actual amount isn't important for understanding the concept. We'll bring back our hydrogen atom. Since it has only a lone proton in its nucleus, there's no energy needed to hold things together. There's only the one thing. So the total amount of energy holding stuff together for these two atoms is 3. When the sun fuses these two atoms together, a new type of atom is produced called helium. As you can see, it has 2 protons and 1 neutron in its nucleus. The energy needed to keep this atom together, though, is only 2. But remember, we started out with an amount of energy 3, and now we're using only 2. So where did the extra energy go? In this case, it's sped away with this expanding wave called a photon. A photon is an electromagnetic wave that has energy and expands outward as a large sphere-shaped wave, carrying away our missing energy of quantity 1. So the total energy is still 3. 2 to hold the new helium atom together, and 1 carried away elsewhere by the photon. But only a small portion of that wave and energy will hit our solar panel on Earth. So we'll illustrate that small portion as this fuzzy wave particle thing. Eventually the energy in that photon is carried up through the interior of the sun until finally it emerges. It then makes its way to Earth and to our solar panel for producing electricity. And now you know the trick that makes fusion produce energy. If you fuse 2 atoms together, then the amount of energy needed to hold the new bigger atom together is less than the total energy that was needed to hold the original atoms together. Well, thanks for watching. I hope you learned something from this video. See my YouTube channel, rimstar.org, for more solar videos like these. You'll find them in the Renewable Energy playlist. And don't forget to subscribe if you like these videos. Bye for now.
Did you know that if the sun were fueled by combustion of, say, gasoline or wood, it would burn out in just a few millennia? So how is it still here after 4.5 billion years? Physics. The sun is like a big nuclear submarine. In the sky. That's right, it's fueled by nuclear reactions that fuse hydrogen atoms together into helium and other heavier elements, releasing huge amounts of energy in the process. In this way, the sun is slowly converting its mass into energy, in the form of sunlight, and it has more than enough fuel to last billions of years. But nuclear fusion's no walk in the park. On Earth, we need to heat hydrogen up 100 times hotter than the sun to get a fusion reaction. So how does the sun do it? Quantum tunneling. There's a small chance, which I'll explain later, that hydrogen atoms, even if they aren't quite hot enough for fusion, will fuse together anyway. And the sun is so big and has so much hydrogen that these small chances happen all the time. And that's what keeps the sun energized. So when the sun shines tomorrow, give thanks to quantum mechanics.
This sun, it is a unique, clean and infinite source of free power, delivering more than 1,000 kilowatt hours per 1 square meter. 1,000 kilowatt hours is the amount of energy found in 100 liters of heating oil. Wouldn't it be wonderful if we could use the energy from the sun? Solar energy, wind power and water energy are forms of very clean energy generation that can be converted to, for example, light. Photovoltaic systems use solar cells to convert solar energy into electrical energy. Solar cells are usually made of silicon, that is a semiconductor material, which means that it can conduct electricity under some conditions but not others. When looking at the periodic table, we see that silicon is part of group 14 and is situated between aluminum and phosphorus. That being the case, a silicon atom has 2 electrons in its first shell. It has 8 electrons in the second shell, but it has only 4 electrons in its outer shell. The outermost electrons are called valence electrons and are of utmost importance because all silicon atoms consist of not more than 4 valence electrons. However, all of the silicon atoms will form bonds by sharing electrons to achieve a full outer shell with 8 electrons, which makes them very stable. In order to disturb the stable state, doping atoms are purposely inserted into the silicon. When boron is combined with silicon, free holes will be created because boron has only 3 electrons in its outer level. With 5 valence electrons, phosphorus creates additional free electrons. And that's where the magic happens. A solar cell consists of 2 silicon panels sandwiched together. One layer is doped with N-type dopants, the other is doped with P-type dopants. To allow an electrical flow of electrons, a front and a back contact are installed to the layers. Glass is installed on top of it to protect the layers and the electrical contacts from damage. Now it's time to take a closer look at the area between both layers. In the N-doped semiconductor, there is an axis of electrons. In the P-doped semiconductor, we observe positively charged electron holes. The electrons in one layer will find their corresponding free holes in the other layer. Consequently, an internal electrical field builds up at this transition that does not permit electrons and holes to jump into the other layer. However, if photons hit the silicon layers, electron-hole pairs will be created. If this happens in the electrical field, electrons are moved to the N-doped layer and holes are moved to the P-doped layer. The system will fall into a state of imbalance because of an excess of electrons in the N-doped layer. The corresponding holes can be found in the P-doped layer. It goes without saying that these free electrons and free holes try to combine. However, the electrical field does not allow such a condition. But if you connect the top layer to the other layer, for example by using a cable, you will see that electrons are traveling to the free holes. This flow is called an electrical current and can, for example, light a lamp. Solar panels can be installed on the ground or on your roof. The solar cells collect the rays of the sun and convert solar radiation into direct current, which is eventually converted into more usable alternating current by a piece of equipment called an inverter. Connected to the inverter is another device that is going to measure the electricity produced by the photovoltaic system. Generated electricity may then be reimbursed by your electricity supplier.
Buildings and generate electricity. Welcome to the future under the sun. The sun is able to produce electricity. Panels covered with photovoltaic cells convert sunlight into electricity. This blue plate is a module made of crystalline silicon. The grooves are the conductors, and the silicon crystals glisten at its surface. To make a solar panel, several modules have to be connected together. Then they apply a soldering flux on each module. The soldering wire is heated with an iron. The modules are placed on a special support. Once the soldering is done, the modules are cleaned by ultrasound in water at 60 degrees centigrade. When dried, the perfectly clean modules are ready to be assembled. Now they can proceed with soldering the modules by groups. First, a flux is applied which improves the quality of the soldering. With great dexterity, they assemble 4 groups composed of 9 modules each. In this way, 36 modules are soldered and connected in series. Modules are assembled end to end. They have to be handled with great care. Using a voltmeter, the voltage of each module is verified. At this stage, it's easy to remake a solder connection if there's a problem. If the voltage is adequate, they use suction grips to make handling of the 9 rows of modules easier and to keep them clean. The modules are placed into position. Then this metallic strip is inserted, which is a conductor that will link the 4 groups of 9 modules. Solder connections are made to link the modules to the metallic strip. Then they put on this transparent sheet of layered glass. It serves as a rigid, transparent form which will support the modules. Superposing of parts forms a laminate which increases the rigidity and solidity of the panel. Finally, a sealing film is applied to protect the module. To laminate and stiffen the solar panel, it's placed in a heated oven from which air has been vacuumed out. The panel will cook at 80 degrees centigrade for 15 minutes. The oven hermetically reseals to proceed with the vacuuming out of air. And here's the finished panel. All the components are bonded together. They now proceed with the test. The panel is placed in a solar simulator. Negative and positive contacts of the solar panel are connected to a voltmeter. The panel is inserted into the simulator and a powerful lamp will illuminate it. The voltmeter is read to make sure that panels supply the electric current required. Here now is the assembly of another kind of solar panel called the amorphous silicon type. Its components were made in Europe and Asia. These here are the positive and negative connecting wires of the solar panel. The panel is placed into a plastic frame and glued in place. Then the frame is screwed tight so that it won't move. The solar panel made up of crystalline silicon modules is put onto an ABS plastic frame. It's now finished. Fabricating this panel will have required about 1 hour of work. 6 of them are made here every day.
Photovoltaic, or PV cells, directly convert sunlight to electricity. Multiple cells are grouped within a structural frame to create a module. When more power is needed than a single module can provide, the modules are combined into groups called arrays. The most common type of module is the flat plate, where multiple cells are encased in clear materials, often made of polymer, placed onto a substrate of metal, glass, or plastic, and covered with transparent plastic or glass. all of which is placed within a structural frame. The second type of module is designed to concentrate the sunlight to improve the output of the PV cells. These are called concentrator PV systems. A concentrator system includes a lens to focus the light in addition to the cells and support mechanism. Modules are combined into arrays to obtain the desired power output at a specific location. The cheapest way of mounting the arrays is to use a fixed mount, which does not allow the array to move. The downside to this is that the array will not be oriented to the sun to receive maximum sunlight as it moves throughout the day. The alternative is to build a tracking system. A tracking system moves the array throughout the day, following the movement of the sun. Tracking systems may be one-axis, which follow the sun's movement from east to west across a single day, or two-axis, which track daily movement as well as the sun's movement north to south on a seasonal basis. Clearly, tracking systems increase output for the same number of cells, and two-axis systems increase output more than one-axis systems. But these advantages must be weighed against the additional upfront capital and ongoing maintenance costs of the more complex equipment. PV arrays may be distributed on individual buildings or centralized into a utility-scale power plant.
Look to the sky. Oh, it's a sunny day. The world is looking so bright. What a surprise. Oh, it's a sunny day. Oh, oh, oh. Give me what I want. I want sunshine, sunshine. Give me, 'cause it's been so long. I want sunshine, sunshine. Summer breeze, oh, it must be magic. I forget all my plans, put my toes in the sand. I just can't.
Before we move on, I want to clarify something that I've inadvertently done. I think I was not exact with some of the terminology I used. So I want to highlight the difference between two things that I've used almost interchangeably up to this point, but now that we are about to embark on learning what voltage is, I think it's important that I highlight the difference, because initially this can be very confusing. I remember when I first learned this, I found I often mixed up these words and didn't quite understand why there was a difference. So the two words are electrical, or sometimes you'll say electric instead of electrical. So electric potential energy and electric potential. And I think even in the last video I used these almost interchangeably, and I shouldn't have. I really should have always used electrical or electric potential energy. And what's the difference? Electrical potential energy is associated with a charge. It's associated with a particle that has some charge. Only that particle can have energy. Electrical potential or electric potential, this is associated with a position. So for example, if I have a charge and I know that if it's at some point with a given electric potential, I can figure out the electric potential energy at that point by just multiplying actually this value by the charge. Let me give you some examples. Let's say that I have an infinite uniformly charged plate, so that we don't have to do calculus. We can have a uniform electric field. Let's say that this is the plate. I'm going to make it vertical just so we get a little bit of change of pace. And let's say it's positively charged. Positively charged plate. And let's say that the electric field, it's constant, right? It's constant, no matter what point we pick. These field lines these field vectors should all be the same length, because the electric field does not change in magnitude. And it's pushing out because we assume when we draw field lines that we're using a test charge with a positive charge, so it's pushing outward. So if I wanted to ask you, let's say I have a 1 coulomb charge. Actually, let me make it 2 coulombs just to hit a point home. say I have a 2 coulomb charge right here. 2 coulombs, and it's positive. A positive 2 coulomb charge, and it starts off, I don't know, let's say it starts off at 3 meters away, and I want to bring it in 2 meters. I want to bring it in 2 meters, so it's 1 meter away. So what is the electric or electrical potential energy difference between the particle at this point and at this point? Well, the electrical potential energy difference is the amount of work, as we've learned in the previous 2 videos, is the amount of work we need to apply to this particle to take it from here to here. So how much work do we have to apply? Well, we have to apply a force. We have to apply a force that exactly, we assume that maybe this is already moving with a constant velocity, or maybe we have to start with a slightly higher force just to get it moving. But we have to apply a force that's exactly opposite the force provided by this by Coulomb's law, right? The electrostatic force. And so what is that force we're going to have to apply? Well, we actually have to know what the electric field is, which I have not told you yet. I just realized, as you can tell sometimes. So let's say all of these electric field lines, I don't know, let's say they are 3 newtons per coulomb. So at any point, what is the force being exerted from this field onto this particle? Well, the force from the electrostatic force on this particle is equal to the electric field times the charge, which is equal to, I just defined the electric field as being 3 newtons per coulomb, 3 newtons per coulomb, times 2 coulombs, it equals 6 newtons. So at any point, the electric field is pushing this way, 6 newtons. So in order to push the particle this way, I have to completely offset that, and I actually have to get it moving initially. I know I keep saying that. I just want to make that point, hit that point home. So I have to apply a force of 6 newtons in the leftward direction, and I have to apply it for 2 meters to get the point here. So the total work is equal to 6 newtons times 2 meters, which is equal to 12 newton meters, or 12 joules. So we could say that the electrical potential energy, and energy is always joules, the electrical potential energy difference between this point and this point is 12 joules. Or another way to say it is this, and which one has a higher potential? Well, this one does, right? Because at this point, we're closer to the thing that's trying to repel it. So if we were to just let go, it would start accelerating in this direction, and a lot of that energy would be converted to kinetic energy by we get to this point, right? So we could also say that the electric potential energy at this point right here is 12 joules higher than the electric potential energy at this point. Now that's potential energy. What is electric potential? Well, electric potential tells us essentially how much work is necessary per unit of charge, right? Electric potential energy was just how much total work is needed to move it from here to here. Electric potential says per unit charge, how much work does it take to move any charge per unit charge from here to here. Well, in our example we just did, the total work to move it from here to here was 12 joules. But how much work did it take to move it from there to there per charge? Well, work per charge is equal to 12 joules per what? What was the charge that we moved? Well, it was 2 coulombs. Well, it equals 6 joules per coulomb. That is the electric potential difference between this point and this point. So what's the distinction? Electric potential energy was associated with a particle. How much more energy did the particle have here than here? When we say electric potential, because we essentially divide by the size of the particle, it essentially is independent of the size of the particle. It actually just depends on our position. So electric potential, we're just saying how much more potential, irrespective of the charge we're using, does this position have relative to this position. And this electric potential, that's just another way of saying voltage. And the unit for volt for voltage is volts. So 6 joules per coulomb, that's the same thing as 6 volts. And so if we think of the analogy to gravitation, we said gravitational potential energy was mgh, right? This was force, this was distance, right? Electric potential is essentially the amount of gravitation, if we extend the analogy, the amount of gravitational potential energy per mass, right? So if we wanted a quick way of knowing what the gravitational potential is at any point without having to care about the mass, well, we would divide by the mass, and it would be the acceleration of gravity times height. Ignore that if it confused you. So what is useful about voltage? It tells us regardless of how small or big or actually positive or negative a charge is, what the difference in potential energy would be if we're at 2 different points. So electric potential, we're comparing points in space. Electric potential energy, we're comparing charges at points in space. Hopefully I didn't confuse you. In the next video, we'll actually do a couple of problems where we figure out the electric potential difference, or the voltage difference, between 2 points in space as opposed to a charge at 2 different points in space. I will see you in the next video.
Who of us hasn't left the TV on even though we're not watching? Who hasn't left the lights on even though we're not in the room? Nowadays, electric power is regarded as a common commodity. Just as the sun rises every day, we believe that electricity is simply there. Electricity appears to be a straightforward issue. You press a button and we have instant electricity. It's as if it's hidden in the socket. But is this really how it is? Just one look out of the window reminds us that electric power comes from somewhere. It travels along the cables on the pylons of the Hellenic Public Power Corporation. If we follow these cables, we might be able to discover where it comes from. In Greece, the largest amount of electrical power is generated in Western Macedonia. 6 in 10 houses get their electricity from the electric power stations in this area. Western Macedonia is the heart of the electrical energy in our country. Let's look then at how electrical energy that we take for granted is generated. In Western Macedonia, there's a large quantity of coal known as lignite. With the use of large machines, it is mined from the ground. Some of the machines are taller than an 18-story building and weigh more than 5,000 cars. After lignite is mined, it is taken to the electricity generating power plants on conveyor belts. In all of the Western Macedonia, there are 270 kilometers of conveyor belts. This is 1.5 times the distance from Florina to Thessaloniki. When the lignite arrives at the station, the process of energy production begins. First, it goes into a furnace burner where it is burned. From the combustion, smoke is produced, which escapes through the stacks of the power station. The burner generates heat, which heats up a large water tank known as the boiler. The water that is heated in the boiler becomes steam. The high-pressure steam goes into a turbine. The turbine has large bladed rotors, just like the sails of the windmill, which, pushed by the steam, rotate at a high speed. In turn, these bladed rotors activate a magnet that generates the electric current. This magnet is part of a device known as an electric generator. Lastly, the steam is separated. Some of the steam is distributed to the surrounding cities and villages via a network of pipes to provide heating. This process is known as district heating. The remaining steam cools, condenses into water, and goes back to the boiler for reheating. Steam is used for chilling by spraying the pipes which convey it with water. The water evaporates and is released into the atmosphere through those characteristically large, thick cooling towers that appear to be forming clouds in the sky. Combustion, steam, turbine, electrical generator, electricity. Once electricity is generated in the power plant, it is distributed all over Greece through cables, which are found on the transmission line towers. It is through these that it arrives in our houses. Highly trained personnel are involved at every stage of the process of generating electrical power. When at some point a conveyor belt tears, the welders are called in. They join additional pieces onto the conveyor belt to make it operate again. When a machine breaks down, the electrician fixes it. Thanks to them, the machines in the plant operate like clockwork. The rope access technicians' work is very difficult. They climb the electrical power pylons to fix them. They change the destroyed cables and join the cut ones. They undergo special training in order to climb the pylon safely. Apart from all the highly trained personnel, there are also the machine operators, the excavator drivers, and the technicians. All of those people work hard so that the power plant operates non-stop the whole day. We saw that in order to have electrical power in our homes, hard work is required by both people and machines. However, the generation of electricity also affects the environment. When lignite is mined from the ground, the natural landscape is destroyed. When lignite combusts, the air we breathe is polluted. The towers that transmit electrical powers to our homes are dangerous at close distances. Furthermore, at some time lignite resources will finish. We estimate that up to now, half of the reserves in Western Macedonia have been used up. This means that in a few years from now, we will run out of lignite. We have already started using other resources of energy, such as the sun, water, wind, and waves. Definitely, the sun will be around for many years, rising daily without our help. In contrast, electric power generation, as we have seen, is a most demanding process. Each time we press a button, let's not forget the long journey made by electric power to our homes.
Hey kids, and welcome to another electricity video. And this one will be focusing more on power, which we kind of mentioned in the previous video but didn't really detail it. Anyway, so first off, what is power? Well, generally it's the ability to do something. If you have lots of power in the workplace, like you're the boss or whatever. But if we look at it in a more electrical or just generally physical term, it's the rate at which work is performed or energy is converted. Basically, in a circuit, it's the rate at which energy is transferred. So if we think about current, The measure of current is how fast units of charge, or coulombs, are moving. Voltage shows how much energy each coulomb has, and power shows how fast energy is going. So it only makes sense for power to be just a multiplication of current and voltage. So basically, what do I mean by the rate at energy in which energy is transferred by multiplying current and voltage? Okay, I'll warn you, this next slide's going to be pretty darn glitchy. So let's say there was a school bus transporting these kids to school. It has 15 kids inside it. Okay, that's your voltage. It travels to school every 15 minutes. Let's say that's your current. If I were to give you an exact measure of current, I'd give you a speed, but that just makes it confusing. So let's just say every 15 minutes. Okay, so then your power would generally be 15 kids every 15 minutes. So your average would be 1 kid in a minute. Okay, so now let's make it 30 kids. Let's increase the voltage. So now it's 30 kids every 15 minutes. So now it's 2 kids per minute. That's your power. Now let's make the bus move a little faster so that it goes every 5 minutes. So that's tripling the current. So now you've got 30 children every 5 minutes. So that means 1 child every 1/6 of a minute. So that's basically your power. So yeah, power is just basically how many joules in a second, or as we like to call it, the watt. That is the SI unit of power. So now let's look at some equations for how you solve power. In the top equation, we have P equals IV. That's basically power equals current times voltage, which of course, as we discussed, makes sense since voltage is how much energy, current is how fast, and power is how much and how fast, basically. Ignore the one in the middle for now. If we look at the bottom, it's power equals energy over time. Now, we said that power is basically the rate of energy transfer. So, the amount of energy divided by how much time it took for that energy to be transferred gives us power. Now, the middle equation kind of mixes a few laws, let's say. If you put power equals current squared times R, or I squared times R, resistance, that basically derives from the fact that voltage equals IR, or current times resistance. So if we look at the top equation, that leads to P equals I times R, or P equals I squared R. If we look at the third part of that equation, it goes to P equals V squared divided by R. And that's because I equals V over R. So if we take the top equation, it becomes P equals V over R times R, or V squared divided by R. Yeah, so just so that you can get another sense of how current and voltage change things, let's see these 4 coulombs pass a single point in the circuit. That's normal. They have normal, let's say, buffness, and they have normal speed. Let's look at the second one with more current. They travel faster, so that's the same buffness, and but more speed. Let's look at the fourth one, which is more voltage. As we can see, the speed is the same as the first one, except this time all the coulombs are generally buffer, or they have more energy. That's just the analogy I use for it. So yeah, that was our very short, very brief presentation on power. I hope you understand everything. I hope you kind of got the concept of power. And Yeah, if you haven't seen the previous video on voltage, currents, and resistance, you should definitely check it out. And just keep waiting for the next video, which will be about circuit calculations, which does sound very boring, but it's actually quite interesting. It's about like how you calculate the total resistance in a parallel circuit, or something like that. So yeah, that's all we have for today. Comment, rate, and subscribe if you liked it, and I'll see you next time.
Now we'll talk about electric power. And when we talk about electrical energy, we inevitably end up talking about electric power because energy and power are closely related. You might remember the formula for power. Power is energy over time. In other words, it's the rate at which energy gets used up. How many joules of energy get used in a given amount of time, in a given second typically. And joules per second is a watt, 1 watt. Or just capital W, 1 joule per second is 1 watt. Now electrically, power is still energy over time. We're just talking about electrical energy now, not kinetic energy or gravitational potential energy. But power electrically is still energy over time. But remember that electrically we have an equation for energy that says energy is charge times voltage. We can use that fact to do a little derivation. Watch this. And you can write this in your notes if you're taking notes on the page. Power is energy over time, and electrically energy is charge times voltage. So we get QV over T. I've just substituted that QV in for the energy. And Q, the charge, is the current times the time. So in place of the Q right here, I'm going to put in IT. So I have the current times the time times the voltage over T. So I've just taken the Q and replaced it with IT. And now when it's written this way, you can see that these T's are going to cancel out. And I'm just left with P is equal to IV. So that's one of our equations for power. P is IV. Write that down, put a box around it. The power is the current times the voltage. That means in any electrical device, any electrical device that has some current flowing through it and has a certain amount of voltage also is using energy at a certain rate. That's the power. And that rate is the rate of energy usage is always current times the voltage. Now we'll do some examples with this, but hold that for just a second. I want to do a little bit more with this equation first. Take this equation, P equals IV, and let's take Ohm's law. Ohm's law says that V equals IR. So let's take that and substitute it right there. And that gives us this. P is equal to I times IR, which gives us I squared R. So that's another equation for power. Now let's do it again. Let's take this equation, P is equal to IV, and take Ohm's law again, but now take Ohm's law written like this. I is equal to V over R. And take this and plug it in for the I right there. And that would give us P is equal to V over R times V, which is V squared over R. So we get two other equations for power that come from thinking about what power is and Ohm's law together. So in other words, we have three equations for power. P is IV, current times voltage. P is I squared R, the current squared, times the resistance. And P is V squared over R, the voltage squared divided by the resistance. And you might ask, well, if you want to find the power, which of these equations do you use? And the answer is simple. If you're given the current and the voltage and you want to find the power, use this equation. If you're given the resistance and the voltage, use this equation. If you're given the resistance and the current, use this equation. So, as is typically the case, you think about what you know, and think about what equations that you know are the case that can apply in that situation. Now here's a simple example. Calculate the resistance of a 40-watt automobile headlight designed for 12 volts. And 12 volts typically is the voltage for electrical systems in an automobile. Well, in this case, we're given the power. 40 watts right there is the power. And we're given the voltage, V. And we're trying to find R, so we're going to use the equation in this form. P is equal to V squared over R. And in this case, we're trying to find R. So we'll just algebraically solve this for R. And we get R is V squared over P. And then we put in the numbers. V was 12 volts, so I have 12 volts squared. And power is 40 watts. So I have 12 squared, that's 144 divided by 40. That gives me 3.6, and that's going to be in ohms. 3.6 ohms is the answer. Here's another example. An electric heater draws 15 amps, so that 15 amps is the current, I. I is 15 amps, and it uses 120 volts, so that's the voltage, V. How much power does it use? Well, if we're given I and V, we can calculate the power using the formula P equals IV. So we just do 15 amps times 120 volts. It's that simple. That comes out to 1800 watts, or we might write it as 1.8 kilowatts. Not too bad.
¿Qué pasó? Oh, the white one? A ver, so.
Alright, yeah, no. I might get electrocuted.
How do you tilt this thing?
Alright.
Hey y'all, this is a video about series circuits. Okay, this is your basic circuit for a series circuit. That's a battery symbol. Come out of your battery to a resistor. A little sloppy here. Another resistor. Another resistor. Okay, that's your basic series circuit. This is E. Make it 12 volts. DC, R1, R2, R3. Now let's say this one's 10 ohms, this one's 10 ohms, this one's 10 ohms. Okay, now in order to find your total resistance, which is R total equals R1 plus R2 plus R3. That's your basic formula. So in this case, R total equals 10 plus 10 plus 10. So R total equals 30. That's ohms. Ohms is your resistance. Now in this case, since you got 3 of them, you could just make it simple and just say 10 times 3 equals 30 ohms. Now this formula stays true in a series circuit. If you have 100, you can have 100, 100 resistors in series, and it's still R1 plus R2 plus R3 and so on. This is only true in series circuits like this. Parallel circuits are completely different. We'll get into that later on. Now to find your amperage, your I total equals I1, which equals I2, which equals I3. In other words, your amperage is the same throughout this whole circuit. So, in this case, you call this I1, I2, and I3, which is your amperage on all three resistors. So I1 equals, okay, first of all, you got to find your voltages. Now, since you know there's three
And when all three resistors are the same, you can do it the easy way. Just say E equals 12 divided by your three resistors, which equals 4. So you'll have 4 volts across each resistor. In the series circuit, your voltages will add to equal your E total. So that's 4 volts across them, like that. Now, you're going to find, I'll show you another way to find your voltage across each one here in a minute. Now that you know your I total, we'll figure your I total. I'm sorry about this, I'm not used to making videos like this. It's E divided by R, E total divided by R total. So your E total is 12 volts, and your R total is 30 ohms. So 12 divided by 30, let me put that in the calculator. You get 0.4 amps. That's your total amperage of this circuit. And since it's a series circuit, it also equals I1, I2, and I3. So you got 0.4 volts, or amp, 0.4 amps coming through here, 0.4 amps coming through here, and 0.4 amps coming through here. Your amperage is the same in the entire circuit. That's just true in a series circuit. Now here's your other way to find your voltage across each resistor. Okay, you got E1, and since you know I and R, look in the book here. It's you can find your voltage, which is R1 times I1. So your R1 is 10 ohms. So E1 equals 10 times your resistance of I1, which is the same as all of them. So it's 0.4. 10 times 0.4. E1 equals 10 times 0.4, which is 4 volts. And if these are different values, you just keep doing the same formula for each one. But since these all three are 10 ohms, it's going to be the same across each one. Like I said, it always adds to equal your E total. 4 plus 4 plus 4 is 12. So that's your basic series circuit here. I'll leave that up there for a few seconds for you to look at. Hope I explained it good enough for you. I'm not always the best at explaining things, so if you got any questions, I'll try to help you. Well, thanks for watching. Catch you all later.
Let's begin by looking at how a simple circuit allows a light bulb to light. A circuit is a route through which electrical current can flow. In our example, electrons flow from the negative side of a D-cell battery to a conducting material on the base of the bulb. From there, the electrons flow up a wire that is inside the bulb and across the filament, which is the part of the bulb that actually lights. When the electrons go through the filament, some of the electrical energy is changed to heat and light energy. The electrons continue down another small wire inside the bulb to another conductor on the base of the bulb. The electrons finally make their way to the positive side of the battery. There would not be a complete circuit if the electrons did not travel to the positive side of the battery, and the bulb would not light. When there is an unbroken path on which electrons flow, as in this example, it is called a complete circuit. The unbroken path that the electrons follow is called a closed circuit, because electricity will only flow on an unbroken path. The light bulb will not light unless there is a closed circuit. Now look closely at the light bulb, and you'll notice that there is an insulator between the conductor that leads up to the filament and the conductor that leads away from the filament. Remember that the atoms of conductors easily accept and pass on electrons. The atoms of insulators do not. As we discussed in the first section of the lesson, electrons will not easily pass through insulating material that surrounds a wire. If an insulator did not surround a wire carrying a current, it is possible for the electron flow to get directed to another conductor that comes into contact with the circuit. Electricity will follow the path of least resistance. If the electrons take a path short of the complete circuit, it is called a short circuit.
Okay. Yeah, yeah. I'm positive. Yeah. Ah! Me quemé. Oh, nice, nice. Shit, what was it? Dude. Shut up! Yeah?
Yeah.
Are you done? Changes.
This is a review about series and parallel circuits. So there are two different types of circuits, series circuits and parallel circuits. In a circuit, the components are joined together by wires. If there are no branches in a circuit, it is a series circuit. However, if there is a branch in the circuit, that means it's a parallel circuit, like this one. More specifically, in a series circuit, there are several components that go one after the other. If you follow the circuit diagram from one side of the battery to the other side, you should pass through all of the different components, one after the other, without any branches. This is how a circuit would be drawn with the components and their corresponding symbols. If you put more lamps into a series circuit, the lamps will be dimmer than before. In a series circuit, if a lamp breaks or if a component is disconnected, the circuit is broken and all the components stop working. Here are some important things to know about series circuits. In a series circuit, the voltage levels can decrease depending on how many components are added to the circuit, but the current will always stay the same. These formulas will also be used to help find the answers to certain word problems involving series circuits. In parallel circuits, different components are connected on different branches of the wire. If you follow the circuit diagram from one side of the battery to the other, you can only pass through all of the different components if you follow all of the branches. In a parallel circuit, if a lamp breaks or if a component is disconnected from one parallel wire, the components on the different branches keep working. And unlike a series circuit, the lamps stay bright if you add more lamps in parallel. Parallel circuits are useful if you want everything to work, even if one component has failed. This is why our homes are wired with parallel circuits. Here are some things to know about parallel circuits. Unlike in series circuits, the voltage level stays stay the same throughout. However, the current will decrease throughout the branches. These formulas will also be helpful to find the answers to certain word problems involving parallel circuits.
When a light goes out in this chandelier, the other bulbs don't go out. When a light in this chain of lights goes out, all the rest of the lights stay lit. And when a light goes out in this room, the rest of the lights in the room remain operable. In these examples, the lights are wired in parallel circuits. In a parallel circuit, different parts of the circuit are on separate branches. Notice how there are a lot more wires in a parallel circuit than in a series circuit. The separate branches allow the current to take several paths in the circuit. In this parallel circuit, if one bulb goes out, the other bulbs stay lit. The circuits in most buildings, including your home, are wired in parallel. Let's now take a closer look at some of the other features of circuits in your home.
Okay, now I want to try and help you understand some of the rules that apply to electricity. First of all, you know what happens when I plug this in. And you may know that what I'm going to plug it into is 110 volts. What's a volt? Well, a volt is a measure of energy. But you'll notice that when I plug this in, something else happened. Current flows through here. We measure current in amperes. You may have heard amps. Somebody's talking about electrical stuff. Amperes run through there. So the voltage makes it flow, and the amperes are the electrons. It's actually how many electrons are flowing. So it's like if I had a tube of water, and if I had the tube perfectly level, the water would stay in the tube. But if I went like this, the water would flow out of the tube. The difference in energy is the voltage, and that's what makes it flow. The actual material is the current. So watch what happens here. I plug this in, and as you sort of suspected, all of the bulbs burn. And they burn the way you've seen light bulbs like that burn. Now let me show you something else that's kind of interesting. These bulbs have relatively high resistance. And what that means is that it's kind of hard for the electrons to fight their way through the light bulb. Here's a light bulb that has a lot lower resistance. It doesn't oppose the electrons as much. So I'm going to take one of these light bulbs out of here. I'm going to put this one in place of it. Watch what happens when I plug it in. Now remember, this one has less resistance. This one doesn't oppose the flow of electrons as much as these do. And look what happens. Wow, a lot brighter, isn't it? Why is it brighter? Because most of the electrons are going through that bulb. Well, you think about it. If you had a choice of going through a place that's hard to go or go through a place that's easy to go, where are you going to go? Most people are going to go through the one that has the least amount of opposition. And that's why light bulbs have different brightnesses.
Okay, now we're going to talk about Ohm's law. Ohm's law is probably the most fundamental equation in the whole world of electric circuitry. Anyone who deals with circuits in any way understands and uses Ohm's law on a regular basis. And I'm going to explain this in the context of a diagram of a simple circuit here. And I'll just draw a battery and a light bulb because, once again, we're all familiar with the batteries and light bulbs. We've seen things like this. So this is easy to understand. Let's imagine a little light bulb here, and we run a wire from the battery over to the bulb, and then from the bulb back to the other end of the battery. And inside the bulb is the filament, and when the current goes through it, it shines. Whenever you have something like this, a circuit element, like this light bulb in the circuit, there are three variables to consider. There's the voltage, and the symbol for voltage is V, capital V. And voltage is measured in volts. So you would say in this case the voltage is 1.5 volts. Or if you have the electrical outlet in your home, you would say the voltage is 120 volts. Unfortunately, the symbol for volts is also V. So you end up writing things like this. You end up writing things like here, V equals 1.5 V, which looks like strange algebra. How can V equal 1.5 times V? That doesn't seem to make sense, but that's not what this says. This is not an algebraic error. This says the voltage, the thing, is 1.5 volts, and this second V over here is the unit. They just happen to have the same letter, but it's pretty easy to tell by the context which is which. So you have the voltage in volts, you have the resistance, and we call that capital R. Resistance is exactly what the name implies. It's resistance to current flow. Everything has some resistance. Well, almost everything. Almost everything impedes the flow of current in some way. And things that you put in the circuit, for example, the light bulb, has a significant amount of resistance. The wires have very little resistance, which is exactly why we use them. In fact, the resistance of the wires is so small compared to the resistance of the bulb that we consider the resistance of the wires to be zero. That's really a good approximation. It's not quite zero, but it's really close. So it's a good approximation to just ignore the resistance of the wires. The resistance to current flow in this circuit primarily comes from the bulb. And anything that you put into the circuit, you could put a light bulb there, a heater, a toaster, anything has some electrical resistance. And resistance is measured in ohms. OHMS, and you recognize the name ohm there. We'll talk about George Ohm in just a second. Resistance is measured in ohms, and the symbol for ohms is the Greek letter omega. This is the last letter of the Greek alphabet, and it looks kind of like a horseshoe like that. So you might say something like this. You might say resistance equals 6 ohms, or the resistance equals 1,000 ohms. That's just how that symbol is used. And then the third thing to consider is the current. And the symbol for current is I. The letter C is used for other things, so that's not the most convenient or intuitive symbol, but just roll with that. Just take that as a fact. Current is commonly represented by the letter I, and it's measured in amps. And the symbol for amps is A, which is kind of nice. That makes sense. Sometimes you hear the term, instead of amps, you hear amperes, and that's the correct term. This is named after a person, André Ampère, a French physicist who did a lot of work with electrical theory at the time this was being discovered. And amps is just short for amperes, and you hear it said both ways, amps or amperes. So someone might write, for example, the current is 5 amps, or they might write the current is 20 amps. That's just how the symbol I is used, and the A is used in this context. I is the current, and it's measured in amps. Amps is the unit. Now, here's Ohm's law. These three things, the voltage, the resistance, and the current, are all related by a nice simple mathematical equation. And this is it. V equals I times R. V is the voltage, I is the current, and R is the resistance. And this equation is known as Ohm's law. And it's not really a law in the sense that it's universally applicable like other laws of physics, but it does work incredibly well for most conductors across a wide range of temperatures and conditions. So this does accurately describe the way things behave in the real world. The voltage flowing through something is always equal to the current times the resistance. Now here's a picture of George Ohm. This guy was a school teacher, and he was conducting electrical experiments, and this was soon after the electric battery had been invented. And before the electric battery, people were only able to do experiments with static electric charges, and they had these little devices called Leyden jars that they could use to store up some pretty big static charges, but it would discharge real quickly. They couldn't do experiments with any sustained current flow. Once the battery was invented, and that was in the year 1800, That allowed scientists and physicists to begin to experiment with a continuous flow of current. And Ohm discovered this in his experiments, this fundamental relationship between the voltage and the current and the resistance. And as I said before, it's one of the most important and most fundamental equations in the study of electric circuits. Now I want to say one more thing about the equation. Ohm's law, which is commonly written like this, V equals IR, can be rearranged algebraically. What if I divided both sides by R? And then you see over here on the right side, the R up top and down below will cancel, and I'm left with I equals V over R. So let's write it like that. I equals V over R. The equation makes a lot of sense if you think about it this way. Remember, well, let me write it over here. I equals V over R, and this is just the original equation, V equals IR, just rearranged algebraically. So I is the current, V is the voltage, and R is the resistance. So think of voltage, remember. Voltage is what motivates the current flow. You increase the voltage, that causes more current to flow. And resistance is that which opposes the current flow. So if you put in something that has higher resistance, that will interfere, that will impede and cause lower current, a lower amount of current to flow. These facts show up mathematically in this equation. You can imagine putting two numbers in here and doing the math, just a division, V divided by R, and getting out a number for I. And this makes sense. If you put in a big number for V right here, then when you do the calculation, you'll get out a bigger number for I, for the current. And if you put in a big number for the resistance, then when you do this calculation, you'll be having a large number be dividing by a large number down here in the denominator. So you'll end up with a smaller value for I. So this makes sense. Increasing, if you understand that voltage is what causes current flow, then you understand that increasing the voltage causes more current. And so putting in a bigger number for V there gives you a bigger number for your current. And if you understand that resistance is interference with current flow, you understand that putting in a bigger number for R will give you a smaller number for current when you do this calculation. So this equation makes a lot of sense, and it also matches what we see in the real world. And that's fundamentally the test for whether or not something is true in science, is does it in fact fit with the actual data that we see in the real world? And in this case it does. Ohm's law, I equals V over R, but more commonly written like this, V equals IR. And we'll come back next and do some simple example problems with this equation.
Hey, it's Dr. Inductor, and now we are going to talk about loads, okay? Alright, so the definition of a load is anything connected to the output terminals of a circuit and affects its performance, okay? I like to think of a load as anything that draws current in a circuit, okay? So if we go by this definition, then anything connected to the output terminals of this circuit would be a load. So let's say we have a just a resistor, okay? That's a load. It's very simple, okay? So if we go by my definition, anything that draws current, then that means that anything connected to a battery is a load, okay? Because everything has resistance. Everything. Alright? So let's say we have a battery here, okay? And just a resistor. Alright? Say it's a resistance of 3 ohms and the battery is 1.5 volts. Okay? I equals V over R, right? So that's 1.5 over 3 fraction. I don't want to do that. Sorry. But yeah, that's the current, all right? It's taking a current. Now if we drop the resistance down to 0, which is impossible. We've not done that before, ever, in the history of mankind. Had a 0 resistance object or thing. Then it becomes